If Angela has $100 to invest at 2.5% per annum, compounded monthly, how long will it take before she has $175? If the compounding is continuously, how long will it be? So we have two separate questions, one where the interest in the account compounds monthly, and then the other where it compounds continuously. And in these two scenarios, we're going to be using two different formulas for compounding interest. When interest compounds a number of times per year, we use the formula A is equal to P times 1 plus R divided by N raised to the NT power. When interest compounds continuously, we use the formula A is equal to PE raised to the RT. Something else to mention is that the phrase per annum means per year or annually. And we'll look at the compounding monthly scenario first, which means that we'll be using this formula. If Angela has $100 to invest, that $100 is the initial principal. If she invests it at 2.5% annually, then what we are going to plug in for R is 0.025 after we move this decimal to the left 2 places. Compounding monthly means that there are 12 compounding periods in the year. So the question is, how long will it take, which means we're going to be trying to solve for T, before her $100 grows up to be $175, which means that $175 is what we're going to plug in for A, the end amount. So let's plug in everything that we've been given. We know that the end amount is $175. What she started with initially was $100. Then we multiply that by 1 plus. We plug in 0.025 for R. The number of compounding periods was 12. And we're going to raise that to the 12 times T. But since T is what we're trying to solve for, that's our unknown quantity, and we hold the spot with a variable in our equation. Now we need to solve for T. So the variable we're trying to solve for is in the exponent position. And when the variable is in the exponent, that means that most likely logarithms are going to come into play. Logarithms and their properties are what enable me to access something that's in the exponent position. So if logarithms are in our future, it benefits us to simplify this equation as much as possible before we bring logarithms in. So the first thing that we're going to want to do is isolate the base that's being raised to that variable power, which means that our first move is to divide off that factor of 100. So on the left-hand side, we're going to get 1.75. And on the right-hand side, we have 1 plus 0.025 divided by 12, and then that's raised to the 12t. Now, I'm interested in knowing what the value of this base is. So let's look at our calculator to see if it's a nice terminating decimal. So we'll say 1 plus 0.025. and divide that by 12, it's not a nice terminating decimal, but I still choose to write it down in order to make the calculations and the handwritten work easier. And when it comes to make our final calculations, we'll definitely use the entire decimal, but for our handwritten work, it's easier to just round it off for now. Now it's time to bring in logarithms because we have simplified and isolated the base quantity that's being raised to the variable power. We can do that by either converting to logs, but I'm actually going to choose to take the log of both sides, and the base quantity that I'm going to choose is the ln. It benefits me to either choose ln or log base 10 because these two buttons are easy to access on our calculator. And now we have the ln of 1.75 on the left is equal to this rounded off quantity, and I do want to keep reminding myself that that's a rounded decimal because at the end I want to use the exact value that's currently sitting in my calculator, so I have the ln of the right side as well. The reason why we bring logarithms into the equation is to gain access to its properties, and the power rule is the one that we're most interested in right now because that's the one that brings that variable exponent down around to the front as a multiplier. So on the left-hand side, we still have ln of 1.75, and on the right-hand side, now we have 12 times t, which is that power, times the ln of this rounded off quantity. We're now trying to solve for t, and in order to do that, we'll need to divide both sides of this equation by the two factors that are connected to that t, which are 12 times ln of the rounded off quantity. we need to divide both sides by those same two factors. And now the 12s cancel out, the ln's cancel out, and I'm left with just t on the right side of the equation, but I'm actually going to switch sides so that it's on the left. And our answer, ln 1.75 over 12 times ln of this rounded off quantity, this is technically correct, but because we're asking for how much time it took, I have no idea how big this number is or how long it'll take when my answer is in this form. So in this situation, it actually is better to give a rounded off quantity as opposed to something that's more exact, because I'm not familiar with how much time this actually is. So we'll go to our calculator and hit alpha F1 in order to get our numerator-denominator function. We'll hit ln of 1.75. Now, 1.75 was not a rounded off quantity. That was something that was exact and terminating, so it's fine to put that in. And in the denominator, we have 12 times the ln of 1.002 was a rounded off decimal. So in order to prevent us from making a rounding error, I want to use this entire decimal quantity, and I can do this a couple different ways. One way is that we could have stored this into x initially and then used that x variable here, but since I didn't do that already, I'm going to use second answer. So second and then the answer function here, which grabs the most recent answer quantity from the calculator, and that would contain all of those decimals. So now I hit enter and see that it takes 22.4 years for the money to grow from $100 to $175. And one explanation for why it takes so long is because the annual interest rate was pretty low. Now the second part of this question says how long would it take if we were compounding continuously? If we're compounding continuously, we need the other formula, the PERT formula. But all these other values are going to plug in the same way. We have P is equal to 100, the annual interest rate is 0.025, we're compounding continuously, not monthly, but we're still being asked how long it's going to take before she has $175. So again, we're going to plug 175 in for the maturity value, which is A. So let's start there. The $100 is the initial principal. E is a constant value. Remember, we never plug anything in for E. R is going to be 0.025, and again, we're trying to solve for T, so that's going to get a variable in our equation, and we're going to try to solve for that T variable. Since we have a variable in the exponent, most of the time that means we're going to need logarithms in order to solve for t. Since we need logarithms, the first thing that we want to do is to simplify the equation as much as possible by isolating the base that's being raised to that variable power. So we want to isolate this bit by dividing both sides by 100. On the left-hand side, again, we have 1.75. That's an exact value, not rounded off. The 100s cancel out, and we now have e to the 0.025t on the right. So we've just isolated that base, and now it's time to bring in the logarithms. Remember, there's two ways that we can bring logarithms into this equation. Number one is that we can just convert to log form, and the other is that we can take the log of both sides. In the first part of this example, we took the log of both sides, so this time, let's just convert it to logarithmic form. When we convert to log form, we start by writing down the word log. And then the base from the exponential form is the base subscript of the logarithm. What we're equal to in exponential form becomes the argument of the logarithm. And a logarithm always has an output that is the exponent from exponential form. So we took the equation that was in exponential form and we converted it into logarithmic form. On the left-hand side, we have the log base e of 175. That's the same thing as the ln of 1.75. So let's use that shorthand notation. And then on the right, of course, we still have 0.025 times t. And now to solve for this t, we're going to just divide both sides by 0.025. And we end up with t is equal to the ln of 1.75 over 0.025. So on the calculator, we'll say the ln of 1.75 and then divide it by 0.025. And we see 22.38 years. Compounding continuously gets Angela to the desired maturity value just a little bit faster then compounding monthly.